Let's see why you might not understand what actually velocity means. So imagine a bus moving on a plane between point A and B. Imagine that it takes 6 seconds for the bus to go from A to B, and A and B are 60 meters apart, just to keep things simple. If I ask you what is the velocity of the bus, you can simply divide 60 meters by 6 seconds, which will give you 10 meters per second. And if I plot this graph of the motion of the bus, it will look like this because the velocity is constant. This is a simpler case. So the distance curve will be straight line, right? But let's see another scenario and notice the speedometer this time. Now, in this case, the bus starts slow, it picks up speed and then it slows down again to stop at point B, right? So if I plot the number which I saw on the speedometer of the bus, that will be our yellow curve, right? In this case, if I ask you what is the velocity of the bus, you might think that let's put the total distance traveled upon the total time taken, and that will give me an answer of 10 meters per second. But as you can see by the yellow curve, that velocity is not equal to 10 meters per second throughout the journey of the bus from point A to point B, right? So let's understand this a bit better. Let's see, what if I ask you what is the velocity of the bus at time t is equals to 3 seconds? So what you might do that, let's analyze from 3 to 4 seconds. So let's say that is my point C and D, and both are 20 meters apart, right? On the graph, it takes 1 second, that is drawn in yellow line, 1 second between 3 and 4, right? And the distance is here, that will be 20 meters. So you might think that let's put the distance upon the time, and that will give me 20 meters per second. But if I plot the velocity graph, the speedometer graph again, you can see there are these many different velocities between time t is equals to 3 second and time t is equals to 4 second. So what's going on? How can we know the velocity of the bus at time t is equals to 3 second exactly? So we know that our answer of 20 meters per second is not correct. So let's say how we can improve our calculation here. One intuition you might have is to reduce the time duration. So you take smaller and smaller nudges in time, the smaller time difference, get the distance and difference traveled, and put it in the equation to get the velocity, right? And you can do this for arbitrarily small duration in time. If you think that the speedometer of the bus is doing the same thing, you would be correct, because this is fine for any practical purpose. So this is what the speedometer might be doing, that it is taking the very small steps in time and getting the change in distance in that small step in time, and then giving you the velocity. In fact, this is what I had to do in order to plot this yellow curve. But as you can imagine, this is not a very efficient way to get the instantaneous velocity at any point in time. And you can also think that this might be not correct 100%, because there is still a gap here. As you can see in the zoomed in scene, there is still a gap between time 3 seconds and 3 plus very small duration in time. So let's say how we handle this efficiently using mathematics, or more precisely using calculus. Let's take a simpler curve to understand the mathematics, the calculus behind this. So I have taken distance curve st equals to t cube. That is to simply say that at any point, let's say time t is equals to 2 seconds, my distance will be q of that. So here 8 meters. So let's see how we can do what's called derivative, taking the derivative of this distance graph to know the instantaneous velocity. Similar thing here, I have taken a small nudge in time dt, and in that small nudge, the change in distance is ds. Now there is nothing special about time t equals to 2 seconds. we can do that at any point in time. For now, let's reduce dt to very small value and have a look. Notice the right angle triangle here. For the highlighted angle, the base is dt and the perpendicular is ds. Notice the hypotenuse, the line which is going over the curve. As the value of dt is very small, the orange line is basically overlapping the distance curve. If I ask you what is the tan of that angle, you will say that is ds over dt. But that is also our velocity. Keep this point in mind, it will just come handy in just a bit. For now, let's calculate the value of ds over dt. We can write the value of ds over dt like this. So that's basically s of t plus dt minus s of t. In our case, the value of t is 2 seconds divided by the small nudge in time dt. Since our distance curve is t cubed, that will change to t plus dt cube minus t cube over dt. And this is simple algebraic expression and we can expand it. Now here, you may think that this is getting messy, but bear with me and it will get simpler really quickly. And you don't have to do this every time. But in order to understand this, this is how things are working behind the scene of calculus. So let's expand it. First term will be t cubed plus 3t squared dt plus 3t dt squared plus dt cubed minus t cubed whole divided by dt. Notice the first and last t cube will get cancelled and we're left with this expression. Now spread the dt from the denominator and you will get 3t square plus 3t dt plus dt square. Notice how the last two value contains dt in them, and that is important. Think about what happens if I reduce dt to a very small value. Basically, we can ignore the last two terms and the value of ds over dt will be 3t square. In calculus, we say that as dt tends to 0. So for curve st equals to t cube, as dt tends to 0, the value of ds over dt will be 3t square, and that is known as velocity. Now notice this orange line. If the value of dt is really small, this orange line is basically intersecting the distance curve at a single point. This line is also known as tangent. Now you might ask, why dt tends to 0? Why dt approaches 0, but why not dt is equals to 0? To understand that, let's have a look at an edge case. Now if I ask you what is the velocity of the bus, or maybe more simpler, is the bus moving at time t is equals to 0? You might do something like this. From the velocity equation, put the value of time t is equals to 0 and you'll get 0 meters per second. But that statement is a bit paradoxical. I might say if not at time t is equals to 0, then when does the bus start moving? The problem arises due to the question, because you are taking this question too literally. So if you can see at t is equals to 0, that statement is instantaneous, and the word moving represents change. By definition, instantaneous means a single point in time, but that change requires more than one point in time. So what's happening there? When does the bus start moving? So you might think it like this, that if I take really small value in time, so let's say 0.001 seconds, the distance covered will be 0.001 cubed, and I will get velocity as a really small value, right? So that means that getting the derivative at t equals to 0 as 0 is not to say that the bus is static there. That is simply, after all, an approximation. If you remember, our dt approaches 0, not equals to 0. So this is still an approximation. And this is how calculus resolve this sort of paradox.